Hello and welcome back to Probability Theory. And as you already know, first I want to thank all the nice people that support this channel on Steady or PayPal. Now in today's part 12 we will talk about the important cumulative distribution function. So here you already see, this is such a long word that often one just speaks of the CDF. Now soon we will see that every random variable has such a CDF. For this, please recall that a random variable just translates from an abstract probability space into a very concrete one given in the real number line. In particular, this could be a discrete probability space where only some values in R are relevant for the probability measure Px. In other words, you can easily embed a discrete set of numbers into R. This means that if you think of both cases we had, so the discrete one and the absolutely continuous one, both are included here. This helps because then the notion of a CDF is exactly the same in both cases. Therefore, I would say, let's define this cumulative distribution function. Here I can already tell you, we will always denote it with capital F, where in the index we put in the random variable x. And indeed, often we will plot the function on the whole real number line. A typical graph could look like this, so it's always increasing. However, it's also possible that it stays constant. Therefore, the first warning here, you should never confuse this with a probability density function, a PDF. Okay, I think that was enough talking here. Let's go to the definition now. The assumptions are the same as in the last video, so we have omega AP as a probability space and x as a random variable. It's not an abstract random variable, but a real valued one. Implicitly, this means we have the Borel sigma algebra for R. Now in fact, this is all we need, and now we can define the function fx. It's important to remember here that the domain for f of x is always the whole real number line. And the possible values lie in the unit interval. So what you can keep in mind is the codomain of x is the domain of fx. Okay, now as you can see in the unit interval, fx is defined as a probability. Namely, putting in a lowercase x into the function is defined as the probability of the interval minus infinity to x. And it's measured with Px, the distribution, the probability distribution of the random variable x. And with this you see, that's the reason it's called cumulative distribution function. So we include here all possible values until we reach the given point x. And here maybe it's helpful as a reminder that this can be written with the original probability measure P. So we have P of the random variable capital X is less or equal than the lowercase x. And we have learned this is exactly the same thing as this. Okay, then this nice well-defined function fx is called the cumulative distribution function of the random variable capital X. Indeed, some people simply call it distribution function of x. Or in short, as I already told you, we just call it the CDF of x. Now, this definition immediately applies some nice characteristic properties for fx. Therefore, let's use a minute to talk about these. They immediately follow because we use a probability measure to define f of x. For example, if we make this lowercase x here smaller and smaller, in the limit x to minus infinity, we would get Px of the empty set. And there we have our important property of a probability measure. The empty set is always sent to 0. Hence, fx has this property in the limit to minus infinity. Therefore, in the same way, we can ask what happens when x goes to plus infinity. There, it's also not hard to see, when x increases, we include more and more in this probability measure. Hence, in the limit, we get here the whole real number line, so we have Px of R. And this is the next important property of a probability measure. The whole sample space is always sent to 1. Okay, so it's not hard to see that we have these two limits for fx. Moreover, we also see immediately that the function f(x) is monotonically increasing. Here, please recall, this means if we go from one point x1 to a larger point x2, the value of the function increases or it stays the same. This follows because the probability measure is always monotonic. This means if we measure a set with the probability measure, then all subsets of this set have a smaller measure or the same. So you see, also this property is not hard to understand. However, now the third and the last property here is a little bit more technical. I say this because it tells us that f(x) is right continuous. This means that in general it's not a continuous function, but it is continuous if you just look from the right hand side. This means we have to look at the right limit here, where x is always larger than the point x0. And then right continuity means that this limit is always f(x) at the point x0. And this is the property we have for the CDF f(x). Now, the meaning of this in the graph you can see above. At each jump point as this one, the filled-in circle has to lie at the upper part on the right. Okay, I don't want to prove the fact here, but you should see the reason for it. We include x here in this interval. And the jump in the graph would mean that the singleton, just with the point x, has a non-zero probability. And this non-zero probability is then included in the whole probability here. Okay, then I think we can look at an example. In fact, this will be one of the most important examples we have. We take the random variable x, which should have the distribution given by the normal distribution. If you have already heard of the normal distribution, then you know it has two parameters. And the simplest case would be that we set the mean to be 0 and the standard deviation to be 1. If you have never seen this, this is not a problem, because now we discuss it. It's an absolutely continuous case, which means the whole probability measure is given by a probability density function. And indeed, this one is given by the famous bell curve. It's not just any bell curve, it's given by the Gaussian function. Which means it's given by e to the power -1/2 x squared. And the correct normalization in front would be given by 1 divided by the square root of 2 times pi. Now, in general, in the case when we have the probability density function, the PDF, we can easily calculate the CDF. In fact, the only thing we have to do is to integrate over the PDF, which means we go from -infinity to the point x. And then we only have to put in the PDF where the constant is written in front of the integral. However, here because x is already chosen as a variable, we need another one. So let's choose t. Now, for the normal distribution, we cannot simplify this integral immediately, but of course we can draw the graph. So we would start with -infinity, then we would increase and increase, and in the end, in the limit, we would go to +1. One important property you see here is because the PDF is symmetric, we will hit 1/2 here. Okay, because my drawing here is not perfect at all, I would suggest that we now go into RStudio. Here, the first thing we should check is the help function, so what is the normal distribution in R? Indeed, here you see we have everything, so the whole explanation what the normal distribution is. Most importantly, we see the probability density function is here given with d norm. On the other hand, the CDF, the distribution function, is given by p norm. And the last one here, r norm, will just give us a sample with respect to the normal distribution. Of course, in addition, you also get a lot of explanations here. Most importantly, you see the definition of the probability density function is also given here. However, you see the parameter sigma and the parameter mu are included here. Nevertheless, the default values are the same as we have chosen. Okay, then I would say we can play around and plot the CDF and the PDF. Now for plotting we need a whole sequence, So let's set x to the sequence where we start maybe with -10 and go to +10 with step size 0.01. Let's hit enter and then we see the result here. Indeed, we recognize that we have 2001 points. Then in the next step, we can put all these points into the density function, which was given by dnorm. Okay, so here you see the best thing would be to enlarge the whole picture. Now, in this picture, we recognize our bell curve. However, maybe it's better to not just plot the values, but also the points x. So we put in x, dnorm of x. And there you see, we have our peak exactly at the point x is equal to 0. Okay, then I would say in the same way, we can plot the CDF. So we take x, pnorm of x. So here you see, this is like our picture from before, but now from -10 to +10. Hence here you can see in the limits, we go from 0 to +1. Now, I would suggest that you play around with all these functions to get a good visualization for the PDF and for the CDF. Okay, now at the end of the video, we can also look at the function rnorm. And if we put in a number, we get as many samples as we want. So in this case, we took 10, but of course we could also take 6,000, for example. So showing all of them is not so exciting, but maybe a histogram is. So let's put in histogram of rnorm 6,000. And here again, we recognize some bell curve. So maybe we can just repeat the whole thing again. And as you can see, we don't change so much. However, maybe we can also increase the number. In another video, I already showed you how you can make a histogram a little bit nicer, and maybe this is something you should do here as well. Okay, now I think that's good enough for this video. I really hope you now know what a normal distribution is and also what a general CDF is. Of course, all questions you can put into the comments, and then I hope I see you in the next video. Bye!